Okay, so I have to keep track of my own talk. So thanks for coming to the last talk of the workshop. I'm going to talk about a joint work with Omid Etesami from IPM Institute and my PhD student Saeed. It's going to be about lower bounds on coin tossing, so coin tossing attacks, how it's related to results in measure concentration, and how it's related to kind of lower bounds in robust learning. So in a sense, it's about how lower bounds in crypto also could play a role in other areas. So it's not going to be a lot of technical proofs, so I hope I can communicate at least what these connections are, what is the main results. So please stop me if you thought there is anything unclear, even though you could also stop me if I was going to talk about proofs, but probably it's even more important now. So I'm going to start by talking about what exactly the coin tossing attack in this work is, like what type of attacks we are talking about, how it's related to measure concentration and robust learning, and a little bit maybe like one slide about the proof. So what kind of coin tossing protocols are we talking about? It is about collective coin tossing. So think about a sequence of parties, n parties, P1 till Pn. They want to collectively agree on one hopefully random bit. And it's a simple model in which there is n rounds exactly, and the ith party sends just one message in the ith round. And the ith message is called xi. When all the messages are sent, the transcript or the sequence of messages is going to uniquely identify the final bit, which we call it f of x. So x without an index is the vector, the whole thing. So x1 and xn are messages. They together determine this message. So it's an online game. It's n rounds. So if the first party sends x1, then the second party sends x2. The third party sends x3, and so on. And eventually, they determine this f of x. And the question is, what if an adversary is basically controlling some of these parties? How robust is this final bit to this corruption? How much can we say that it is robust? So I'm not quite formal about the last line. So what is the exact attack model? How is the adversary basically choosing these corrupted parties exactly? What is the limitation? So that's the next slide. So before going there, if there is a question about the kind of non-attack version of the story.
This is with broadcast, right? You broadcast.
Yes. So the corruption is going to be a subset of parties, and we want to be robust. The attack model. First of all, the adversary here is really interested in making the output to be 1. It's not like the typical coin tossings where we want to attack by either pushing it up or pushing it down. If I increase the probability of 0, it doesn't help. It doesn't count. It's not an attack. So the adversary really has a preference to increase the probability of 1. So it makes the job of the attacker a little bit harder. I want the attack to be polynomial time. You can ask information theoretic questions also here, but I'm particularly interested in polynomial time attacks, which makes it also a little bit harder. But I'm going to allow a pretty relaxed notion of corruption that this time comes to help the attacker. So it's called the strong adaptive corruption model, which allows the attacker to choose which parties to corrupt as the game goes on, even after seeing what message they were about to send. So the adversary can wait and see the message of the party number I, and based on that, choose to corrupt the party. Then the adversary is somehow paying a cost because he has corrupted one party. So kind of animation-wise, the second party is about to send this message x2, but the adversary looks at it and then chooses to corrupt that party, substitute the message with x2 prime, and now everybody else doesn't know what x2 was. Everybody gets to see x2 prime. And x3 is about to be broadcast. The adversary gets to see that, doesn't do anything. x4 is about to be sent. Adversary actually chooses to corrupt this party, substitute it with x2 prime, and so on. So this is the attack model. If you have any question about the attack model, maybe we can take it now before going further.
Everyone send just one message in order.
Yep.
And if they don't send the message,
And then
if you abort, then this is just a default message.
there is no abort, suppose. Or you can interpret abort as a special message. So the main question is, if the adversary wants to increase the probability of output being 1 to be pretty close to 1, say 90%, almost bias it completely, how many parties the adversary needs to corrupt? And the result is that you can actually do it with a root n number of parties, roughly. So you can corrupt root n number of parties and make the output to be almost always 1. In polynomial time, exactly the way I described it. Now I'm going to talk about a little bit of kind of related work, the context. There were some problems that were studied related to this. I'm going to go through them quickly. Unfortunately, I don't have time to talk. There are a lot of interesting books in coin-tossing attacks. We have experts here like Eran, Iftach, Yevgeny. But the type of results that I'm going to go over are going to be two results that are very closely related to this, very kind of similar models. Yes?
So do you assume on F that it's polynomial time computable?
I assume F is polynomial time. I assume the F originally is unbiased and is polynomial time computable, but the attack only needs oracle access to F. So somehow it is still meaningful if it's not. Any other questions? Alphabet is arbitrary. So two related results very quickly. Well, before that, I'm not familiar with my slides, evidently. So the main result is kind of more, just to put it in the format that I said. So PI sends an arbitrary long message xi in round I. Adversary is corrupting the square root of n parties and is making the output to be completely 1, even though it was 50-50 at the beginning. Adversary is polynomial time. But adversary is deciding to corrupt the party number I after getting to CXI. So this is a strong adaptive corruption. The first 3 properties are good for the attack. The last one is somehow a bad property of the attack. But the thing is that the applications that I want to talk about, they all imply because of the good properties. And we are somehow compromising on the last line, but that's OK for those applications. So that's how we could basically get a new coin tossing attack by compromising here, but still getting those applications from the attack.
So is it obvious that it's stacked, like majority is stacked?
So it somehow shows majority is tight, but yeah, it's another way to show majority is tight.
Is it like an open problem to relax this task, or do you know that it's not possible?
To relax the task of?
The fourth point.
You cannot do it. Even in unbounded time, if you allow arbitrary long messages, it's not possible to do. You have a single, because you can have like a version of AND function where the bits are biased and you have an AND over biased bits, like you can call it tribe function, or you can have a function which even in exponential time, you cannot do much if you want to increase the probability of 1. So that's the thing. I want really the attacker really needs to increase the probability of 1. And then you can prove that the last line, the relaxation here is needed.
So what is the answer if the last line becomes smiley face? If the last line is a smiley face?
Then you have to change the attack model. You have to either go to bitwise, or you have to allow the adversary to win by pushing it up or down.
No, but if you fix alphabet size,
Alphabet size is fixed, but I'm saying it only works for Boolean. Basically, for the applications, it's crucial to have all those 3 properties. So maybe we can discuss about the other versions later. OK, so previous work. So Liechtenstein lineal stacks in '89, a seminal work. They studied the problem for the bitwise setting where the uniform bits are being sent. And this work and the other works that I'm going to mention, none of them are polynomial time attacks. So that I will not even mention. So they're all exponential time attack, but there are even more restrictions to them. So they studied bitwise setting where people send bits. They showed indeed that you can corrupt root n number of people and bias the bit to be almost always 1. So the first one is a bad property. The second one is a good one because they didn't need a strong adaptive corruption. The more recent work, which is actually an inspiration, we use ideas from this work of Kalai, Komargotsky, and Raz. They studied arbitrary long messages, but then they had to compromise for either biasing the function up or down. And this is a good thing or a bad thing, but we get polynomial time and we get both of them good, but we compromise on a static or on a strong adaptive corruption. So I want to now move on to show why this simple, seemingly kind of very clean result in coin tossing can give you surprisingly surprising consequences in areas that don't seem to be really about crypto and how to use them to do other stuff. So I'm going to show a computational version of measure concentration to be employed basically by this simple coin tossing attack. So I want to, this is now changing, a little bit change of topic, but this is something not very complicated. So let me go over this slowly with you. This is a classical result in concentration measure literature that has many forms. You can look at it as an isoperimetric inequality or just a concentrational measure. It's called blowing up lemma in the information theory community. But this specific version is from the famous paper of Talleyrand. And it says, suppose you have a product distribution. So mu is a distribution over n coordinates, and you're sampling each coordinate independently. So that's how I represent it as product. And you're comparing two inputs or two vectors based on their Hamming distance in that large alphabet. You just count how many different locations, how many locations they differ. And that's how far these two vectors are. That's your metric. So you have a distribution. You have a metric that tells you also how far things are. And you have a specific set S that is not very small. So the probability of getting sample in this set S is epsilon, and epsilon, for example, is non-negligible. It's like 1 over poly n, n is here the dimension. So you have a metric probability space, product space, Hamming distance, and you have an initial set S. So the theorem says that in high dimension, when n is large, most of the points in the space are actually close to S. Doesn't matter which S you choose. As long as S is not tiny, is not exponentially small, counterintuitive thing is that almost everywhere you're going to be close to S. So 1 minus delta fraction of the points, once you sample from this product distribution, has distance k from your set S, and distance to set S means like your closest neighbor in the set S. And if you look at this bound, it's not linear, it's kind of root n. So, putting parameters there, if you put epsilon to be 1 over polynomial, then 99% of the points are within almost root n distance from whatever set you choose. It doesn't matter what set it is, as long as S is not very small. Okay? This is a generalization of Chernoff bound, for example. Chernoff bound says if you look at the product distribution where these are just uniform bits, and if you look at the set S to be things that have summation at most n over 2, then you're going to be almost root n close to that set. You can derive Chernoff as a very special case of this. This is kind of a generalization. But what we ask, so pictorially, you have a space here. Every point here is a vector. It's a vector of dimension n, and you have a set S which is not too big. But once you look at things that are close to S, it covers almost all the space. So you ask an algorithmic version of this problem. What is a natural algorithmic question here? So this theorem only tells you that being in S and outside S is large. So suppose you have actually suppose you have a way to tell whether you are S in or not. So somehow you have some efficient way to tell whether you are in S or not. A search version of this problem is to actually find the close neighbor in S. So you are given this. So this mapping tells you that if you sample a point, there is going to be a close neighbor, but it doesn't tell you where it is. It's just an existential proof. It's based on basically some form of isoperimetric inequalities that don't tell you how to go back. So the question is basically algorithmically find such close neighbors in S when you're given a random point. What is the problem again, just to formalize it? So you have this product space. You have these independently sampled coordinates. You know that if there is any set S which is not too small, once you freshly sample a new point, there is this proof by Talleyrand or others that tell you there exists a close neighbor in the set S. Now we are asking, please give me an algorithm that finds it. So I give you Oracle access to S. I was going to tell you in a minute, but you asked it. So S is not a small set. S is not a small, so I cannot give you everything in S. If I'm going to algorithmically ask you find a neighbor in S, I have to give you implicit representation to S. I give you Oracle access. You ask me a query, I tell you if it's in S or not. So the job of the algorithm is basically solve this problem. You have this product distribution. The set S is not small, is non-negligibly large. You're given a fresh sample from the space. You want to find a close neighbor in S. And answering your question, you have formally Oracle access to S. But you need actually more than that, because you might also ask, how do I sample from this distribution? Well, I also give you a sampling oracle. So that was also something you would need. No, not from a sample, freshly sample from the whole space, which you can use to also get samples from S, because S is not very small. S is only 1 over polynomial.
But do you need sampler for the whole mu or for restrictions?
Doesn't matter, because they're independent, so they're equivalent. If you have sampler from, it's a product distribution, so you can say I have an oracle that gives you fresh sample from the whole distribution. It automatically means you have it for every coordinate.
So the product distribution is essential here.
It is essential here.
Everything is given as oracle, just finding any point close to X, not any other point close to X. But in the distribution is hard.
Well, you can find a close point to X by just perturbing X a little bit, but you would not fall into S. So there are 2 trivial algorithms. None of them do everything. So if you freshly, you can actually, as Luca pointed out, you can indeed sample from X. But if you do it naively, we can prove that if you just do this simple trick, I keep sampling and keep trying. I keep sampling things from S. I want to know how close I would be. You would actually end up being always far. So you have to do a structured search. You really have to do a search algorithm here. If you naively just sample things in S, you'll end up being theta and far. So that's not going to help you. So you have to somehow start from the point and kind of change it a little bit and eventually find a neighbor in S. Is the question here clear? What's the algorithmic question here? If mu is arbitrary, you might not even have the information theoretic concentration. But you can ask the same exact question in any concentrated metric probability space. So if you have an information theoretic guarantee that there exists such a close neighbor, not necessarily for product distribution and Hamming distance, the same exact question you can ask, and I'm going to talk about it very briefly. But for now, I'm going to just show you how to solve this one. Is the question clear? So I'm going to just reduce it to the coin tossing problem in 1 line. So I'm going to give a coin tossing protocol that if you attack, you will basically end up finding such close points. How many parties did I have there? N parties. How many coordinates do I have here? N. So I will have the party number I independently sample a message from the distribution di and broadcast it. That's my protocol. It still is not complete. I have to say when is the final output bit 1, when it's 0. So if the output falls into the set S, I will call it 1. If it was outside, I call it 0. Now, what's going on now? I want to basically change some of parties' messages by corrupting them so that after, you can imagine that the protocol is being executed honestly. If it was honestly, it means you're going to get a random point in the space, and you would have, some probability of falling into S. We want to now perturb that vector by changing a few coordinates of the parties so that now the output is going to be one with high probability. That's exactly what we wanted to do.
But now it's not half, though.
Well, our CoinTossing attacks actually works even if it's not half, and that's actually crucial. To go below, for example, 1/n, it needs a lot of work. So our algorithm, so that's the technical kind of running time. The running time of the attacker is polynomial n over epsilon. So if epsilon here, which is the probability of the set S, if it was 1 over polynomial, I end up with a polynomial time algorithm, which is fine. And it changes square root of number of parties messages, and it ends up basically giving you something in the set S. This is exactly the mapping we want.
You could have a lot more powerful approach, right? You can look at the entire coordinates.
Indeed, we didn't. Another thing, our attacker ends up being online, even though we didn't need it to be online. We could have looked at everything, but for some reason, I have no idea how to think. If I try to kind of improve it, we could not improve it by using that.
How many oracles? So your guy can make only n oracle calls?
No, polynomially many queries.
Also polynomial.
So when I say polynomial time, it implicitly bounds the same number of queries by the time. Okay, so this is the result only for product distributions. But how about other concentrated distributions? Actually, you can look at the literature, pick your favorite high-dimensional metric probability space. It's likely to be concentrated. Like if you look at Gaussian with L1 norm, L2 norm, they're all going to be concentrated pretty much with the same parameters. They have even one name called normal Levy family when they have kind of similar behavior. So I only talked about this one, but indeed, you can prove we can define and prove this algorithmic version of measure concentration for other metric probability spaces as well. We can be lazy as usual, try not to do things from scratch, so we can actually do reductions as well. So you can define some form of algorithmic reduction between metric probability spaces that tell you how to go from computational concentration of one space to computational concentration of the other one. If you look at the paper which is now online, we formalize this. And for example, we look at proofs that are previously done for reductions in the information theoretic setting. Then you can point out which new components you need, which kind of sampling properties you need to add so that you get also computational version of concentration in the other space. So for example, we do it based on this paper from 97. And one more comment about it. The typical way that concentration is stated in the literature is not the way I did. It's based on concentration around the expected value. Like you have a function, you want to concentrate around expected value. So you have like tail bounds. You can indeed define algorithmic version of it also that you want to find a close point to your original point by having a small perturbation that now it falls into kind of this expected value region. So there is a way to formalize it. For some problems, it becomes trivial. Like the Chernoff itself, it's kind of trivial. You can do it because of the Chernoff itself. You have a trivial algorithm that does it. But there is still non-trivial problems there once you have this function that you want to kind of prove the concentration around is given to you as an oracle. And there are indeed, like Mac-Diarmid inequality or others that you can ask the question and it's non-trivial, but you can do a reduction to the version that I said in one line also. So you can, so the version that we solve is the stronger one algorithmically. You can derive the algorithmic version for concentration around mean as well. So now just very briefly, I want to, without getting into details, I want to show you that this computational concentration of measure that came from our CoinTossing attack, you can immediately apply to attack other things. So for example, you can attack robustness of learning algorithms, the way that is an active area. People attack, we call it lower bounds, they call it attack. One reason is that when you call it lower bound, you have to prove it for you have to prove a theorem. You have to write it more generally, so it's harder. But once you call it attack, you can just attack somebody's algorithm, and you just have to run something and have a table. So that's how you can have 10 more papers that way. So let me just tell you what this basic setting is, how in one line basically you can get an attack with a proof as a bonus. So suppose you want to do pack learning for a classification problem. What is it? What is the problem? There is the distribution over the inputs, D. You have a label for that instance called C. You have this example, a bunch of them, D1 till Dm, all of them given to this learning algorithm that outputs a hypothesis that later on is supposed to now predict the label of a fresh sample once you give it to it. So it's basic problem in learning. We want to have high confidence in producing something that has high accuracy. What is a poisoning attack that is being studied? It's very relevant to Valiant's model of kind of noise from a long time ago. It's being kind of reformulated in this fancier term. But pretty much it means that you have a same story, but the training set is not really all honestly generated. Some fraction of the training data is coming from an adversary who has arbitrarily substituted them with something malicious. You want to know how robust your algorithm is to this perturbation. How much can you still claim to be high confidence and high accurate? So suppose now the adversary wants to mess up with this process and make the learning algorithm output a hypothesis that has some bad properties. What is that bad property? I leave it abstract. For example, maybe you want that particular hypothesis to give loan to your cousin, or some specific property that you want to make the learning process be influenced to kind of suffer from. So you have a set of bad hypotheses. The adversary wants to kind of push the hypothesis, end up being in that bad, vulnerable set of hypotheses. So the theorem that you can get immediately is that basically the adversary can tamper with root m, number of the training examples, and increase the probability of that bad event from any non-negligible probability to go close to 1. You need...
So if the learning algorithm is randomized?
No, that was my next one. So you need to assume that the learning algorithm is deterministic. You also get a version of it for other types of, you get it also for the other types of attacks that are called evasion attacks, or adversarial examples is the hotter. There also you need some form of deterministic assumption to basically get a similar theorem. So proof by picture, like probably some of you already see the proof because you see that Luca even pointed out something that I want to get after that. So the proof by picture is that you have this space of training sets that is kind of a product set. So every point here is a vector of length m. And your learning algorithm is deterministically mapping it to this set of hypotheses. Some of them are bad. You look at the pre-image of what training sets were leading to that bad hypothesis. And the concentration, first of all, tells you that you're going to be close to a bad training set anyway. So that's an existential attack. But you can make it also polynomial time because of this result. And the attacker needs to have this oracle access to this fresh sample. So the attacker needs a bigger data set somehow to run this attack in polynomial time. And it has extra features that actually are meaningful in that context. The attack is online. There are papers studying online poisoning attacks. The attack, interestingly, ends up not using any wrong labels, because what is the attacker doing? The attacker is substituting a coordinate with another coordinate, but it stays in the support set of the distribution. I haven't even defined what is outside the support set. So support set of this distribution means still another example which is still correctly labeled. So somehow doesn't use any wrong labels, only uses them against the learning algorithm. Okay, so just one slide on the proof ideas, because that text is surprisingly not very complicated. And by the way, because it's not complicated, you get also alternative proofs to those measure concentration results, even if you're interested in the information theoretic version. So this is the main result again. So you have a coin tossing attack. The PI party sends one message arbitrarily long. You want to corrupt root n of them in polynomial time and bias the output completely. How do you do it? The description of attack is simple, so I can describe it and in one slide. So the attack is online. Of course, it's an online game. You have I-1 parties already have sent their message. Now the next party is about to send. The next party is about to send. So I'm very tough on myself, evidently. Or maybe not. So the corrupt party, we want to decide to corrupt party PI, if this XI is a good candidate to be substituted. So in one sentence, we will substitute this XI with something else. If it basically has a good influence of the output, that's a good investment if it can basically influence the final output. But the technical term is that it should be a multiplicative influence, and it should be in retrospect after knowing Xi. So these are, of course, we should look at Xi and then see whether it's an influential thing to change, and it should be multiplicative. So just formally speaking, you look at the expected value of falling into the right region, which is the output being 1. Suppose alpha is the expected value condition on this very message Xi, and suppose alpha star is the expected value for a different message Xi prime. So if you can find an alpha star that is much better than alpha, then it's a good idea to corrupt this party and and change the message. But the kind of technical thing is that we don't look at additive distance, we look at multiplicative distance or the ratio. And we choose this kind of threshold of when it's a wise thing to actually corrupt this to be 1/√n. And then pretty much everything works fine. So that's at the high level the description of the attack. So the analysis is basically using some simple potential functions. So I'm not going to get into it. It's not very complicated. And we learned it from the security community because you should give a name to your algorithm. There is a study showing if you give a name to your robot, people would have even human feelings toward them. So we have this Musio algorithm, multiplicative conditional influence optimizer, and how it's related to the previous works. If you use additive version, basically you end up with ideas used in the paper by Kalai, Komorogowski, and Raz. But we want, as I said, we want to go outside additive. And the additive version was also used in a previous work with my student Saeed. We again got stuck at this kind of threshold of concentration of like 1/√n, but we wanted to prove it for a non-negligible. And that's where we came up with this multiplicative version that basically sorts everything out. You can get all these tight bounds. So that's pretty much it. And we had this connection from coin tossing to computational concentration and going to robust learning. But if you like coin tossing, we can go back and study versions that Yevgeny Gaskin and others. And that was pretty much it. If you have any questions, let me know. But thank you for this talk and also for staying for the whole workshop. Yes. So if there is any question for the speaker, let me know. Otherwise, I have some announcements. So basically, just a quick reminders. We don't have a lot of long closing remarks. Basically, thanks you for coming to the workshop. If you don't mind filling the surveys that Puya mentioned, we're going to send a reminder, but that would help us if you organize something to do it better, or we can give the feedback to you for you helping do something better. And if you have some pictures that you thought it's okay to share with us on the page, if we get nice pictures, we will add them to the workshops page to stay there. We have one at least, it's because we took the collective picture, but if you had more, please share it with us. Other than that, thanks for your time and hope you enjoyed the workshop, and hopefully see you on another lower bound or another workshop in Bertinoro maybe. Anyway.